Today we learn about another kind of population growth called exponential. So last class we learned about linear growth models where you add the same amount at each transition. Linear growth results in an arithmetic sequence. In an exponential growth model, you multiply by the same amount at each transition. And exponential growth results in a geometric sequence. Here's an example of exponential growth. The Earth's population was about 6 billion in the year 2000. Assuming the population doubles every 45 years, let's project the population in 2045, 2090, 2450, and 2900. So if it doubles every 45 years, 2000 to 2045 is 45 years, so it should double to 12 billion. So my population, so population in 2000 is 6 billion. Population in 2045, 45 years later, it should double to 12 billion. And the population in 2090, it should double again because 45 to 90 is another 45 years, so now it's 24 billion. Now 2450, the population in 2450, I need to know how many sets of 45 have passed since the year 2000. So I'd say, okay, well, 2000 to 2450 is 450 years. Divide that by 45, and I get 10 sets of 45 have passed. That means my 6 billion people will have doubled 10 times. So I start with my 6 billion, and I have to do times 2, times 2, times 2, times 2. I have to do 10 of these, right? To multiply by 2 10 times to double it 10 times, which is the same thing as 6 times 2 to the 10th. So let's see what that is. 2 to the 10th times 6 is 6,144 billion people, which would be 6,144,000,000,000 people. All right, and then in 2900, the population in the year 2900, well, 900 years have passed since the year 2000. Divide that by 45 because it doubles every 45 years, and you get 20. So I have to do 6 times 2 times 2. I have to double it 20 times. Right, so that's actually 6 times 2 to the 10th, because repeated multiplication is an exponent. Sorry, to the 20th. Doubling 20 times now. Okay, so 2 to the 20th times 6 billion is, wow, 6291456 billion, right? I don't even know if I could, billion, so the 291 is trillion, so 6 quadrillion, 291 trillion, 456 billion people. A lot of people. Okay, can you figure out what the Earth's population was in 1955? Well, that's before 2000. How long before 2000? So 2000 minus 1955. Oh, it's exactly 45 years before the year 2000. All right, so P of 1955. Well, if you go forward 45 years, you double. Going backwards 45 years should halve your population. So your population in 1955 should be 3 billion people. 1820, population in 1820. Well, let's see, 1820 is how many years before 2000? So I do 2000 minus 1820, 180 years before 2000. So how many sets of 45 is that? 4. So I need to start with my 6 billion and halve it. I have to do 6 billion times a half, times a half, times a half, times a half, right? Because I'm having 4 times to go back 180 years. So that is 6 times 0.5 times 0.5 times 0.5 times 0.5 is 0.375 billion, which means 375 million. All right, 1100, that's way, way back. Population in the year 1100. Well, 2000 minus 1100 is 900 years. This is 900 years in the past. Divide that by 45, that's 20 sets of 45. So I have to take my 6 billion people and have it 20 times. So I'm going to multiply by a half 20 times, which I could write as 1/2 to the 20th. So I do my 0.5, I raise it to the 20th, because the order of operations says to do the exponent first. So 0.5 to the 20th, and then multiply that by 6, and I get a teeny tiny number, 0.0. Let's see, how many zeros? 1, 2, 3, 4, 5 zeros, and then 5722. Billion people. So if I want to know how many actual people that is, it's actually 5,722 people total. Seems like there were more people than that in the year 1100. It's probably not a great model to go that far from the year 2000. All right, a harder question would be to figure out what was the world's population, or what will it be in the year 2120. So let's see, how many years is that from 2000? It's 120 years. 120 divided by 45 is 2.6666, right? 2 2/3. So let's see if this works if I do it the same way. The population in 2120, it's harder than the other problems because it's not being doubled an even number of times. So I can't just multiply by 2.6666 times, or can I, right? I'm going to say, well, let's start with my 6 billion and multiply by 2 repeatedly. And how many times? Well, 2.67 times. And yeah, we can do exponent of 2.67. 2 to the 2.67, and then times 6 billion is 38.19 billion people. So even if I don't have an exact multiple of 45 years, I can solve the problem the same way that I was doing it before. All right, let's look at a population of rabbits. It starts at 1,000 and increases by 20% each year. Let's find out how many rabbits there are after 1 year, 2 years, 3 years, n years. So 1 year, so we'll say p sub 0 is 1,000. That's our initial population. 1 year later, to increase by 20%, I have to keep my original amount, 1,000, plus 20% of 1,000. Or I could say, well, take my 1,000 and multiply it by 1.2. The 1 because I'm keeping 100% of my original 1,000, and the 0.2 because I need 20% more. So P1 is going to come out to 1,200 rabbits. And then P2, I would say, well, take the 1,200 that you had in your previous year and increase that by 20% by multiplying by 1.2. All right, 1,200 times 1.2 is 1,440. 1,440 rabbits. P3 is going to be however many I had in the previous, increased by 20%. So I multiply by 1.2. And I get 1,728 rabbits. So after n years, P sub n would be my population from the previous year, P sub n minus 1, times 1.2. So there is a formula, that's my recursive formula, because it uses the number of rabbits from the previous year. An explicit formula would say, okay, well, I'm starting with 1,000 rabbits, and I'm multiplying by 1.2 over and over and over again, which is an exponent, n times. This is my explicit formula. The number 1.2 in this problem, it shows up in the recursive formula and the explicit formula. Okay, it's called the common ratio because it's the value of the ratio of the current population to last year's population. So to confirm this for the first few years, if I do the current population to the previous population, I get 1.2. Current population to previous population, 1.2. Current population to previous year's population, 1.2. So that's why it's called the common ratio. And here are the general formulas for an exponential growth model. Again, you don't need to memorize these because we just did a couple of examples where we wrote formulas without knowing this, but they can be handy. So for recursive, give a starting amount, and then P sub n is equal to P sub n minus 1 times the common ratio. And for explicit, P sub n is your starting amount times the common ratio to the nth power. All right, lastly, I just want to mention that exponential growth is generally not sustainable since resources like food and water and space are always finite. So you can't just keep doubling a population forever. A more realistic population growth model is the logistic curve, which levels off at the carrying capacity of the environment. So the curve looks something like this. You won't be tested on logistic growth. I just thought you might find this interesting. So that's it for the lecture portion of this lesson. You can now start your activities and let me know if you have any questions.